Hi everyone, this is Xiang, and I'll be talking about our work on scaling back-propagation by parallel scan algorithm. This is a collaboration between me, Yifan, and my advisor Gennady. We published and presented this work in MLSys earlier this year. To kick off the talk, let me present the high-level ideas of our work. The back-propagation algorithm, or BP in short, is a popular way to train deep learning models and was implemented in many frameworks such as PyTorch and TensorFlow. However, BP imposes a strong sequential dependency along layers when calculating the gradients, which makes it very hard to parallelize. To address such strong sequential dependency, we propose scaling BP by parallel scan algorithm, or in short, BPPSA, which basically means to reformulate BP into a scan operation, which is a parallel computing primitive that produces partial reduction on a sequence of elements. And afterwards, we can leverage the parallel algorithm to scale such reformulation on parallel systems. Our method ends up with a logarithmic steps instead of linear along the critical path of the dependency, and in some extreme cases, we were able to achieve a backward path speedup as high as 108x, which leads to an 2.17x end-to-end training speedup on our RNN benchmark. Let's look at some background starting with BP. BP is used during training specifically for providing the gradients to almost all well-known first-order optimizers such as SGD and Adam. It has been implemented in almost all modern deep learning frameworks such as PyTorch, TensorFlow, and IMAXNet. However, despite the popularity, BP still got a fundamental problem, and let me explain what it is. Given a function that takes a vector and produces another vector along with its Jacobian matrix, in case if you forgot, a Jacobian is essentially the partial derivatives of each output element with respect to each input element. BP states that the gradient of the input is calculated by multiplying the transpose Jacobian with the gradient of the output. And the neural net is essentially a composition of vector functions. So in this simple example here, the gradients at every layer are calculated by Jacobian gradient multiplications one layer at a time recursively. And you can probably tell from this animation that there exists a strong sequential dependency between layers during the gradient computation. We can choose to respect such dependency, and that's exactly what data parallel training does. In this case, BP's dependency is preserved in each node, and training is scaled up by stacking more and more nodes, which essentially increases the batch size. It is conceptually simple, and perhaps that's why it's widely used. However, the scaling of such approach does not persist forever due to the phenomenon of generalization gap and batch size scaling limits. More importantly, the model must fit into one device. And if such constraint cannot be fulfilled, you probably need to use model parallel training instead. Model parallel training essentially partitions the model and distributes the parts among devices. However, BP's strong sequential dependency would be problematic because one device must wait for the next one to finish processing the gradients. This prior works on pipeline parallel training to mitigate such problem, and it even works practically up to a certain level. However, it has its own limitations nonetheless, which are linear per device-based complexity and the trade-off between bubble of idleness and potential convergence effects. One thing prior works have in common is that they treat BP as a black box from an algorithm perspective. However, problems with strong sequential dependency were studied in the past, but in a much simpler context. By using the prior wisdom, we dig into BP itself and try to open this black box by proposing a novel way to scale BP by parallel scan algorithm, which contains three key ideas: reformulating BP as a scan operation, scaling BP by a customized Blelloch scan algorithm, and leveraging the sparsity in the Jacobians for more optimization. At this point, you might be wondering what scan is. Given a binary and associative operator such as addition, as well as an input sequence such as from 1 to 8, scan computes the partial reductions at each step of the sequence. So in this case, 3 is the summation from 1 to 2, and 10 is the summation from 1 to 4. Before I get into more details about scan, let me first define three key terms. Steps refers to the executing the operator such as addition once, N refers to the number of elements in the input sequence, and P refers to the number of workers which are instances of execution. For example, a worker could be a core in a multi-core CPU. With only a single worker, scan is executed linearly, which takes n steps. However, can we achieve sublinear steps when more than one workers are available? There actually are a few parallel algorithms to do that, most famous of which is the Blelloch scan algorithm. Blelloch scan contains two phases. In the first upsweep phase, it computes partial sums via a reduction tree. And in the second downsweep phase, it combines the partial sums across branches to cover all possible outputs. It is important to highlight that each level can be done in parallel given enough workers. Therefore, because the reduction tree has logn depths, it should be very obvious that Blelloch scan takes 2 logn steps along the critical path. Now let's look at how we can use the knowledge about scan in the case of BP. The key insight of our work is that matrix multiplication in BP is also binary and associative. Therefore, by replacing the addition with an operator that multiplies two matrices in reverse, and replacing the scalar inputs with the final gradient vector and the transpose Jacobians at each layer, we can reformulate BP as a scan operation which produces the same output as BP. And of course, we could use the same Blelloch scan algorithm to reduce the number of steps on the critical path from linear to logarithmic. Since matrix multiplication is not commutative unlike addition, we need to customize the downsweep phase to accommodate such property. However, Jacobians are conventionally perceived as very expensive to handle, since its growing pace is the product of the pace of its input vector and the output vector. For example, the Jacobian of the first convolution in VGG11 on separate 10 images occupy more than 700 megabytes of memory. More importantly, the Jacobian is conventionally generated one row at a time by passing the basis vectors into the backward functions of each layer, which is very slow, as you can probably tell from how long this animation takes. As a result, conventional ML algorithms try to avoid using Jacobians directly, the same way this cat ditches the stinky feet. Despite the popular belief, we observe that the Jacobians of many operators are very sparse. We can visualize the Jacobians for convolution, ReLU, and max polling operators, where the yellow dots represent non-zero values and the others are zeros. As a concrete example, we list the sparsity of the first three operators of VGG11, and they are very sparse. More importantly, the purple dots are what we call guaranteed zeros, in the sense that their patterns are deterministic and their positions are known ahead of training time, and they come from the mathematical properties of the specific operators. In the case of ReLU, it is because ReLU is an element-wise operation. Therefore, such properties could be used for better sparse gem performance. And instead of generating the Jacobian row by row, we develop an analytical routine that generates them directly into sparse formats such as CSR, and that leads to a very significant speedup. Now that we've finished talking about the method itself, let's take a look at how we can evaluate it. The simplest way to evaluate our method is through an RNN, which is known for having the problem of performance bottleneck by long sequential dependency. And we synthesize bit streams to let the RNN classify between them. We evaluate on state-of-the-art Turing architecture GPUs, and we use cuDNN's RNN backward pass implementation as our baseline since it is widely used, and we use PyTorch as our experiment frameworks. We implemented the Blelloch scan algorithm as custom CUDA kernels. To simplify the presentation, the following results are from the 2080 Ti platform. We perform end-to-end training with the batch size of 16 and the sequence length of 1,000 and plot the training loss curve with respect to the walkout time. As you can see, the blue curve, which is our method, is essentially the red curve, which is a baseline scaled down horizontally. Note that even though our method produces the mathematically equivalent gradients, there might be numerical differences due to the Jacobians being multiplied in a different order. This figure here confirms that such numerical differences do not affect convergence. And we can observe a 2.17x overall speedup in this case. Afterwards, we perform sensitivity analysis by varying the sequence length, which reflects the model length n, and look at the backward path speedup. BPPSA scales with the model length initially until when there are not enough workers, and we can also observe a speedup as high as 108x. We also want to analyze the sensitivity of how the performance of our methods varying with the number of workers, and we demonstrate this by varying the fraction of GPU per sample. As we increase the fraction of GPU per sample initially, we can observe our method scales with the number of workers p until there are more than enough workers. There are more results in the paper, which includes sensitivity analysis on 2070 versus 2080 Ti, end-to-end benchmarks of GRU training on the IRMAS datasets, as well as the pruned VGG11 retraining on the Server 10 datasets. To conclude this talk, BP imposes a strong sequential dependency among layers during the gradient computations, which limits the scalability on parallel system. To address such dependency, we propose scaling back-propagation by parallel scan algorithm, which includes 3 key ideas: reformulating BP as a scan operation, scaling BP by a customized Blelloch scan algorithm, and leveraging the sparsity in the Jacobians for further optimizations. Our methods achieves logarithmic steps instead of linear on parallel systems, and in the extreme cases, our method is able to achieve up to 100x speed up on the backward pass, which leads to an 2.17x overall speed up on our RNN benchmark. That's the end of my talk, and I'm open to questions you may have. Thank you.